So when we learned about how water moves from an area of high concentration to low concentration, that's one thing that plays a role in the way it's going to move. Another thing that plays a role in the way it's going to move is pressure. And those two things together comprise what we call water potential. And so let's write some definitions about what water potential is. So water potential is a measure of the energy available for water movement. All right, so it measures the ability of water to move always from areas of high water potential to areas of low water potential. And the two things that play a role in the direction in which water is going to move are pressure and solutes. And so the psi here is the symbol that stands for water potential. So I'm just going to put underneath it what it means. So normally we wouldn't write water potential underneath it. Equals. And so there's two things that play a role. The pressure, this is called the pressure potential. Plus the solute potential. So psi sub s stands for the solute potential. Again, we would not normally write these things in there, but that's what those mean. And so that's our equation. So what we're saying here is that the potential of water to move from one area to another plays a role is how much solutes there are. So remember, if there's 0 solutes, then it's 100% water. And the pressure, if the pressure builds up, if you squeeze and put pressure, it increases the likelihood that water will move from one place to another. And so let's write underneath here that pure water, pure H2O, at atmospheric pressure, that means just the normal pressure at atmospheric pressure. That means that at just the normal pressure that the atmosphere puts on things on the earth. So the atmosphere normally is putting pressure on things on the earth, and so that's normal, and so that's at what we call atmospheric pressure. So just pure water at atmospheric pressure has a water potential of 0, meaning that there's no additional pressure and there's no solute potential. All right, so there's no solutes, so it's pure water. All right, and so both of these values would be 0, no solutes, no pressure, water potential is 0. So let's write there, no pressure and no solutes. All right, so let's take a look at each one of these things and talk about what a solute potential is and what a pressure potential is. So let's start out with solute potential. So solute potential which is the psi with the sub s. So what is that? So let's write a few things about it. First thing, let's put a little bullet here. It is the effect that solutes have on a solution's overall water potential. So let's talk about that. If the more solutes water has, what does that do to the likelihood that water is going to move from one place to another? Well, adding solutes, remember, lowers the water concentration. The more solutes you have, the lower the water potential. So let's add that here. So the addition of solutes lowers the water potential of the system. All right, so let's look at this mathematically. So if water potential is pressure potential plus the solute potential, and solutes always lowers the potential for water to move because it lowers the concentration of water. So if solutes always lowers the water potential, what kind of number mathematically does this solute potential need to be? A positive or a negative number? So mathematically, to lower this would have to be a negative number. So let's add that to our thing. So the solute potential is always negative. So I'm going to add here, remember, pure water has a water potential of 0. So that's 100% pure water, no solutes. So any solutes whatsoever will make the solution have a lower or more negative water potential. Because we're starting out here, pure water has 0, so if you add solutes, that's going to lower that, so therefore be a negative number. So when we look at that equation, water potential is pressure potential plus solute potential. The solute potential is always going to be a negative number, which will always lower the potential of water to move. All right, the second thing that plays a role in which direction water is going to move is the pressure potential. I should have wrote that down a little bit there. Okay. So let's do the same kind of thing and write some bullets underneath here. So pressure potential is the effect that pressure has on a solution's overall water potential. So if there's any pressure whatsoever, so if there's no pressure, the pressure potential is 0. If there's any pressure whatsoever, is that going to increase or decrease the likelihood that water is going to move? If you add pressure to a cell, squeeze it, it's going to increase the likelihood that the water is going to be squeezed out of the cell. So any pressure is going to increase the water potential. So therefore, pressure is always going to be what kind of number? Positive or negative? It's going to be positive. And so let's write that here. An increase in pressure an increase in pressure, let's write potential, results in a more positive value and a decrease in pressure. Let's see, I'm running out of room down here. Let's go to another page here. A decrease in pressure potential results in a more negative value or closer to zero. All right, if there's no pressure whatsoever, your pressure potential is zero. So therefore, let's, underneath there, let's continue on, because remember we were putting bullets, all right, under pressure potential. So pressure potential, psi sub p, is usually positive in living cells, and if there's no pressure, it's zero. So water potential is pressure potential plus solute potential. So pressure potential generally is positive. Any kind of pressure is going to increase the likelihood that water is going to move from one place to another, and increase, therefore, the water potential, the potential for water to move. So it increases water potential. So let me give you a couple of examples utilizing this information. So the first one, example number 1, I'm going to draw a little setup here. So you have a beaker with water that's open to the atmosphere. There's no top on this beaker. And you have, let's say, a piece of potato or a potato cell. We'll just call it a potato cell. I'm going to make it big here. All right. And you have, this is pure water. All right. And so let's say that this is at the beginning of our experiment. So you put the potato in and into 100% pure water. So let's talk about what the water potential, remember water moves from an area of high to low water potential. So therefore, let's look at this equation. Water potential is the pressure plus the solute potential. So if we look at this, what's the solute potential? Is there any solutes in this? In this water? No, it's pure water. So therefore the solute potential is 0. And it's open to the atmosphere. There's no pressure here. It's just open to the atmosphere and just exposed to just normal atmospheric pressure. What I mean by, like, exposed, like, to the atmosphere, no pressure. So this is just atmospheric pressure. Imagine what pressure would be is if you put like a plunger in here and pushed down on that plunger, then it's going to put pressure in this water and increase the likelihood that water will go into the cell. All right, so that's additional pressure. This is just open to the atmosphere, so therefore the pressure is 0. So remember back when we wrote over here that pure water at atmospheric pressure has a water potential of 0, no pressure, and no solute. So that's what we're looking at here. So whenever it says it's open to the atmosphere, the pressure is 0. All right, so then the potato cell. Now the potato cell, when we look at here, let's say we have the water potential is pressure plus the solute potential. And let's say you're given that the solute potential is -3 and there's 0 pressure, and so therefore the the water potential is -3. The water potential would be equal to the solute potential in this case. So what does this -3 mean? Obviously, the higher the number there, the negative means that it's lowering the water concentration, that there's solutes, and so that's what the negative means. And then the higher the negative, meaning it means the more solutes that are dissolved. And so therefore, obviously, a potato cell is not going to be 100% pure water, so it's going to have some solutes in it. So therefore, water goes from an area of high water potential to an area of low water potential. Well, the water potential for the pure water, I guess I didn't finish that, is 0, because 0 plus 0 is 0. So, and then the water potential for the potato cell, because of the solutes, is -3. -3 is lower than 0, so it goes from a high water potential to a low water potential, and water will move into this potato cell. So then, let's look at the end here. So this was the beginning of this, and then let's look at what happens at the end. And so in this case here, now we still have the beaker, and we have our potato cell in it. And so we still have pure water on the outside. Let's say nothing diffused out. So we still have pure water with a water potential of 0. All right, then how do I got that? Because water potential plus pressure plus solute potential is 0 plus 0. And so that's how I got that and arrived at that. But now the potato cell, when we look at the potato cell, it originally had the water potential at -3, but what happens is when water goes into that cell, what happens to the pressure? It's going to start going up. And so what happens is that will continue to go in until the water potential equals the outside solution. So in this case here, eventually at the end, and where the diffusion, the net diffusion, oops, kind of losing my focus here, where you get the end of the net diffusion of water inside the cell is when the water potential is going to equal the water potential on the outside. So when this water potential equals 0. And so therefore, in order for that to happen, if your solutes stay in the cell and your solute potential is -3, water will continue to go in until that pressure builds up, and that pressure equals a value that's going to make the water potential at 0. So therefore, this is where it would reach, stop the net diffusion inside. And so we would say the water potential is the same inside and outside the cell. Excuse me. And therefore, there's no net diffusion. So then let's add to that. All right, so let's look at example number 2, and let's add solutes. We're going to add solutes to the water outside the potato cell. So let's look at this setup here. All right, so here's our setup, and let's write some things here. So here's your solutes in the water. So we look at the water potential as pressure potential plus the solute potential. And this is exposed to the atmosphere, so your pressure is going to be 0. And then now we added solutes, so it's not going to be 0, the water potential, because you have solutes, and that lowers the water potential. So let's say it's -12. So I'm giving you this. So the water potential is -12 for the solute dissolved in the water. Let's talk about what's going on with your potato cell. So water potential is pressure potential plus solute potential. Let's say the solute potential for this cell is -15. So what will happen is, at first, if water goes into the cell, if there's no pressure, then the water potential would be -15, and then so therefore -12 is a higher number than that. So the water will go in, and as the water goes in, that pressure builds up until, I'm going to put here the pressure at 3, until it equals -12. 12. All right, and so in combination with the solutes and the pressure, eventually you get a combination where the water potential is equal to the water potential outside. We would call this that these two, the cell and the solution, are in dynamic equilibrium, where you're not going to get any more net water movement into the cell due to the pressure buildup, even though the solute concentrations, if we look here and here, the solute potentials aren't equal. So here there's more solutes dissolved in the cell than outside the cell. So the solute concentrations aren't equal inside and out, but because of that pressure buildup for that water coming in, that plays a role in the net water movement and therefore eventually can cease to occur. And so, and kind of resist that water coming into the cell. And so let's write over here to the right of it. So the water potential inside and outside are equal, but the solute concentration, I'm going to put the brackets, solute concentrations are not equal because the water potential inside the cell is a combination of both the solute potential and the pressure potential. So therefore, you can have a situation where the concentrations aren't equal on either side, but the water potentials are, because the other thing that plays a role in the diffusion of water is pressure. So therefore, as the cell fills up with water, there may not be any more room, the volume, the space that's filled to the max with water, and so therefore net water diffusion will cease to happen. So one other thing that we need to talk about is how to actually calculate, how do they get this solute potential? Like when we say up here that the solute potential is -3, there's actually an equation that is involved with that. So let's write here, calculating solute potential. All right, and so this is the equation. Solute potential is -ICRT, where, and then I'm going to give you an example, or tell you what these things are. So where I is what we call the ionization constant. And it's it's the number 1 for sucrose, which we're going to use in our labs. Sucrose is not an ionic compound, so it doesn't dissociate into ions. So when you put sucrose, which is a disaccharide, into water, it stays as one particle because it does not ionize or dissociate into water. Example 2 for sodium chloride. Why? Because sodium chloride dissociates when you put it into water. It doesn't stay NaCl, it dissociates into Na plus and Cl minus. So it dissociates into 2 ions, and so its ionization constant will be 1. For most of what we're going to be doing, it'll be, 2. For most of what we're going to be doing, we'll, in our lab, we'll talk about it with sucrose. So the ionization constant would be 1. But the second common one would be sodium chloride, which would be 2 because it dissociates into 2 ions. Now, what does the C stand for? C stands for the molar concentration of your solution. Of the solution. And this is measured in moles per liter. So that's what the big M stands for. Like when we say 1 molar, that means 1 mole per liter. R is a pressure constant. And this is the value 0.0831, and these are the units: liter, bars per mole Kelvin. Kelvin is a temperature range, or way to measure temperature like Celsius. I'm sure you remember that from chemistry. And then T is the temperature in Kelvin. And how we get Kelvin, you probably remember it's 273 plus whatever the degrees Celsius is. So you add 273 to that. So then when we look at this, we have two constants, ionization constant and pressure constant. And so these guys, the I and the R, are going to be pretty much the same. So the only variables are going to be C, the molar concentration, and T, the temperature. All right, so let me give you an example of a calculation in which to do this. So let's write a question here. Here's our question. What is the solute potential of a 0.15 molar solution of sucrose at atmospheric pressure at 25 degrees Celsius? All right, so that's our question. So therefore, we're looking at what is the solute potential. That's what we're solving for. So we're going to use this equation. So let's rewrite the equation. Solute potential is negative I CRT. And so, what do we know? So let's write down here what we know. All right, sucrose. Sucrose is not an ionic compound. The ionization constant is 1. So negative, and there's no units on that. So I'm going to put negative 1. Then the C. The C is the molar concentration of solution. So I said that it is 0.15 m molar solution. So therefore, remember this though, we have to write it in moles per liter. So 0.15 molar solution is 0.15 moles per liter. And so that's what I'm going to do here, 0.15 moles per liter. So that's my C. Then I have my R. R is my pressure constant. This is always going to be the same. So let's write that. I'm going to 0.0831, and it's liter bars over per mole Kelvin. So that's my R. And then T is, remember, it's temperature in Kelvin. So they gave us, I gave it to you in 25 degrees Celsius. So it's Celsius, so we have to add 273 to that. So 273 plus 25 gives us 298 K. All right, so that's what I have. So then let's do some dimensional analysis with crossing out our units. And so notice here we have mole, mole, liter, liter, Kelvin, Kelvin. So what is going to be my units for the solute potential? It's going to be in bars. So I take negative 1 times 0.15 times 0.0831 times 298 gives us what? And if we calculate all that out, we're just going to round to the hundredth. It's negative 3.7, and our units are bars. All right, so that is the answer to my problem about what is the solute potential. So therefore, when we go back and look at some of these other things that we drew, that's how they get this -3 for a solute potential and so on. So these are the pieces of information that they would need to know, all right, to figure that out. So that's how we calculate that. This is not an equation that you have to memorize, but you need to know, we need to know how to manipulate it. And I'm going to give you some more practice problems in class with that. So let me ask you this. If this is exposed to the atmosphere, the solution, all right, it says it is the atmospheric pressure. That's my clue that it's open to the atmosphere. So I have a solution that's open to the atmosphere. What is my water potential? Water potential is pressure potential plus solute potential. What is my water potential? Can you answer that? Well, we know our solute potential is negative 3.7, right? And our pressure potential, if it's open to the atmosphere, is 0. So therefore, your water potential is going to be the same as your solute potential because it's open to the atmosphere and there's no additional pressure. All right? And that, my friends, is water potential. Okay?